Welcome to the glass plate again. In today's example, we're going to think about manufacturing, or rephrased, cooling of a manufactured presse-papier. That basically is a big sphere of solid material, and we will take that it's made of perspex. Presse-papier is used to put on a stack of paper so that the sheets don't fly away if somebody opens a window or a door. In our case, we'll use a presse-papier that is made at about 100 degrees, and when you take it out of the production line, we will assume that its initial temperature is still uniform and is about 70 degrees Celsius. The outside temperature is 20 degrees Celsius, so there is a driving force and the sphere will cool down. The question we would like to answer is, how long does it take before the average temperature is 30 degrees, and what is then the center temperature? We're going to do this by assuming that all resistance to heat is inside the sphere, so that the boundary of the sphere is at 20 degrees. In practice that will not be the case, but for first estimates we will assume this. This is clearly a case of heat conduction. Heat from the inside has to move outside. It's clearly also unsteady, as the temperature of the perfect sphere will need to change from 70 to 30. Moreover, we can quickly grasp that this must be long times. For short times, only the boundary of the sphere will have changed its temperature, and by no way can we expect that the mean temperature will then have dropped so much towards the outside temperature. So what we have is unsteady conduction from a sphere, and it is long times. This means that we can use the graphs with confidence. The graphs basically shows us lines of, for instance, the average temperature as a function of the dimensionless temperature written here over the Fourier number, which equals AT over D squared. Thus we can anticipate that we need to find A. Well, for perspex, lambda is 0.2 watt per meter Kelvin, rho is about 1200 kilo per cube, Cp is, I looked up on the internet, 1466 joule per kilogram Kelvin. Okay, from these we can compute this thermal diffusivity A. A is for perspex, I did it, 5.7 10 minus 8 meters square per second. Now we have all the ingredients. All we need to do is pick up the graph, calculate this number, read off the line. So what we're going to do, calculate this number, read off the line, find the corresponding Fourier number, and back out with A and the diameter, the time required. Okay, let's do the analysis. D is 10 centimeters. I compute this value given that I need 30, so this is 30, 20, 70, 20, hence I need to read off my graph at 0.2. So I pick up the graph, here it is. I have computed this number, I read off at a value of 0.2, and I take the line of the sphere, I go down and have a value of 0.025 in the middle of this gap for the Fourier number. So I read off and I get that this is 0.025. Thus I find the time from AT T over D squared. The Fourier number is 0.025. I'll move over to the side so that you can read. And thus the time equals 4400 seconds. Remarkably long, but it's a relatively big sphere. Okay, that is answering this question. How long does it take for the mean temperature? Quite a bit over an hour. Now for the center temperature. For that, I need the second graph. The second graph I need to read at the dimensionless time 0.025, because then the average temperature is 30 degrees. If I do that, now I do it the other way around, I read off here, find the line for the center line, and see that its value is 0.5. Actually, if I read it carefully, at this I do the center temperature dimensionless. It is 0.7. And thus I find that the center temperature itself is 55 degrees Celsius. Okay, let's recap what we had. I realized that it is pure conduction from the inside towards the boundary. Resistance, heat transfer on the outside neglected. Temperature is 20 degrees. It is unsteady conduction of a sphere for long times, as the entire sphere needs to cool down significantly. For that I use the graph, compute from the known, the question 30 degrees, the dimensionless temperature, back out the dimensionless time, fill in the number, find that it takes 4,400 seconds. At that dimensionless time I read off the center graph and I find that the dimensionless temperature of the center equals 0.07, and out of that I get the center temperature is 55 degrees, lacking behind quite a bit compared to the mean, as we have already guessed, of course, because the center is the slowest one to respond. This shows you, with a simple example of cooling down a spherical object, how you can use our unsteady long-term graphs. See you at the next one.